Hey there, Gregory Carlson here for the Calculus Building, and we are going to be looking at some more chain rule examples. And oftentimes the chain rule can be combined with other rules like the product rule, the power rule, and the quotient rule. And sometimes it's a little bit tricky about which one to do first. And so you kind of want to look at the big picture as we're taking derivatives of things and and just be careful to take the derivatives one piece at a time. So I'll show you a few examples. In this first one, it would actually be easier to move this denominator to the numerator and make it have a power of -4. But I've already done an example like that in a previous video. So what I'm going to do here is I'm actually going to use the quotient rule. And we know that the quotient rule is low d high minus high d low all over low squared. Now, it's really important that you only do the chain rule when you are taking the derivative of something that needs the chain rule. And so you'll see what I mean as we go through this example. So we do the low times the derivative of the high. So the low times the derivative of the high, which is 0. So notice I did not need to do the chain rule here because all I had to do was just copy paste the low. I didn't take its derivative, so I didn't need to do the chain rule here. Minus the high times the derivative of the low. So now we are doing the chain rule. So that would be 4 times 5x minus 7. Leave the inside alone. We can knock the power down by 1. And now we would multiply that by the inside of the parentheses. So we would multiply that by the number 5. Now, do I need to do the chain rule on this part? I add low squared. And the answer is no. I don't need to do the chain rule because we're just squaring the low on this step. And so we're not taking the derivative of it here, so I don't need to do the chain rule. So in reality, in this problem, I only needed to do the chain rule one time, and that's when we did the derivative of the low. That was the only time I needed to do the chain rule. So let's simplify this a little bit. By the way, this is equal to dy dx. So all of that's going to go to 0. And let's see. Let's just rewrite this. So on the top, I have 5 times 4. I'm going to have 20 times 5x minus 7 to the 3. And here we have a power to a power, so that would be 5x minus 7 to the 8. And that simplifies. 3 of those are going to cancel, so that becomes a 5. So the final answer is dy dx is equal to 20 over 5x minus 7 to the 5th power. And there you go. So the moral of the story is be careful to only do the chain rule when you're A, taking a derivative, and B, taking a derivative of something that has a chain in it, that you need to take the derivative of the inside function. So let's do an example of the chain rule and the product rule. So here I have x times x squared plus 4 to the 3. So we're going to use we can't just distribute this x because I have a power of 3 right here. So we're going to use the product rule, and remember this part we can call f, and all of this part we're going to call g. And as a reminder, the product rule is f prime g plus fg prime. So let's be careful here and think about when we need to use the chain rule. So first I have f prime g, so the derivative of x is 1 times g. Do I need to do the chain rule there? And the answer is no, because I was taking the derivative of f. I wasn't taking the derivative of g, I was just copy-pasting g. Now with the product rule we add, and we do f times, all right, now I am taking the derivative of g, so we will need to use the chain rule. So that's going to be 3 times x squared plus 4. So bring the 3 down, and I have x squared plus 4, leave the inside alone, and that 3 power gets knocked down to a 2, and then you multiply by the derivative of the inside, which is going to be 2x. Okay, so that's what this would look like. Again, we only did the chain rule once, and that's when we were taking the derivative of the second part of the product rule. So let's simplify this a tiny bit. Not much we can do. This is going to be x squared plus 4 to the 3. And over here, 2x times 3. That would be 6x squared times x squared plus 4 to the 2. So I would stop and leave my answer right there. If you wanted to, you could FOIL this all out and maybe put it in standard form if you wanted, but for our purposes, I think that's good enough. So we had the chain rule inside of a quotient rule and the chain rule inside of a product rule. Let's look at a slightly different example. Notice this one. On a previous one, we had the chain rule as part of the quotient rule. But this time, if you notice, the chain rule is the outside function. And so the quotient rule is going to be the part of the chain rule. So here's what I mean. The derivative of this is going to be take the derivative of the outside and leave the inside alone. And then we bump that power down by 1. So we just took the derivative of the outside by using kind of the power rule, and we did -5 minus 1, which gave us -6. And now with the chain rule, I need to do the derivative of the inside. And what do we have on the inside? That's right, we have a fraction. So now we're going to need to do the quotient rule. So that is low times the derivative of the high, which would just be 5, minus the high times the derivative of the low, which would be 3. Okay, so that's low d high minus high d low of the top, and on the bottom we would have low squared. And so there's your derivative. What a complicated looking derivative, but we were able to calculate it pretty quickly, all things considered. You could simplify this a bit. You could do distributive property up here and clean this up. Also, you could flip this, which would turn this -6 to a +6, and you could cancel a few of the 3x plus 4s. So you could simplify this a little bit, but I'm just going to leave it right here. I don't doubt your algebra simplifying abilities, so I'm just going to leave that problem right there. I'm really happy if you can get this derivative. Let's see, I think I have time for one more. So we're going to find dy dt for the pair of functions. And notice that I have y in terms of x, and I have x in terms of t. So I don't have y in terms of t. And so I just don't have that, so I'm going to use the Leibniz notation. What I do have is the derivative of y with respect to t would equal dy dx times dx dt. So if I multiply the derivative dy dx times dx dt, these are related rates, and that would give me dy dt. So dy dt equals, we want to take the derivative of this with respect to x, and that would be 2x minus 7. Okay, so that's this derivative. And let's multiply it by the derivative of x to t. And so the derivative of this with respect to t would just be 2t. So that's almost the answer. We really want y in terms of t, so the last thing to do is to just substitute this x for t. So the final answer would be dy dt is equal to, and what I'm going to do is I'm going to replace this x with what x is equal to. So that's going to be 2 times t squared plus 4 minus 7 times 2t. And so there, let's clean that up a tiny bit. So that's going to be 2t squared. Here we would have plus 8 if you did the distributive property. So plus 8 minus 7 would be plus 1 times 2t. So that's dy dt right there. 2t squared plus 1 times 2t. That relates y with t by going through the variable x. Another way you could have done this one, just for the record, is you could have substituted t squared plus 4 in for here and in for here, and then just taken the straight derivative, dy dt. And so you should go ahead and try that on your own just to see that we get the same answer, but I guarantee you that you will. And that's why calculus is so much fun. You can always do these problems one way or the other. have a few more examples to go through, and then we'll be done for a while with the chain rules. So I will see you in the next part. If this video was helpful, please don't forget to share it, like, and subscribe. See you in the next video.